So, good evening, everyone. Today we'll start with the ligand substitution in square planar complexes. Last class we talked about the substitution reaction. Uh, Today we'll particularly focus on ligand substitution in square planar complexes. So, in this chapter, we will understand the mechanism of the substitution reactions in trans and cis complexes. We will discuss the isomerization of complexes with chelates, mostly that involves the Berry-Sido rotation mechanism. We will understand the substitution reactions of square planar complexes, and also we will discuss the different factors that affect the reactivity of square planar complexes. That also includes the Swain-Scott equation. So this is the basic outline for today's class. And first, we will start with the stereochemistry of reactions. So first, to begin with, for particularly for square planar complexes, stereochemistry is actually important because it has been generally assumed that the reactions with mechanisms where we have dissociation mechanisms, they mostly undergo isomerization or racemization. So because such type of reactions they undergo isomerization or racemization, we see there is a change in the stereochemistry of the reactions. So here, single product reactions may occur where the configuration is either retained. So what are the possibilities of the stereochemistry of the reactions that undergoes such type of ligand substitution reactions? So what happens is the configuration it might be retained or the configuration it might change. So this is the for two cases possible cases, and in most of the cases it has been observed that the configuration changes. Like for example, when we consider the hydrolysis, base hydrolysis of cis cobalt diethylenamine dichloride in dilute uh, zero point 0.1 molar OH minus solution, that is hydroxide solution, then we see the cis form. Whereas, but when we take a concentrated hydroxide that is greater than 0.25 molar solution, then we see CN ethylene diethylene diamine plus OH2 complexes formed. So this is the ligand substitution reaction. And although here we see the stereochemistry remains the same, but the substitution reaction it has occurred. So in both these situations, the mechanism should be of a conjugate base, that is the protein is first removed from the en ligand, that is the ethylene diamine nitrogen. We have the ethylene diamine ligand where there is two nitrogen atom, and from the one of the nitrogen a proton is removed during the hydrolysis, after which the chloride that is trans in position to the deprotonated nitrogen, it then goes away. So the concentration of ion pairs, that is the cobalt diethylene diamine dichloro OH minus, it is more in the concentrated base, and thus the water molecule it is produced from the OH minus and H plus is removed, where because it has been placed in such a way then the chirality is inverted. So here you see how the product it has been formed with the retention of product, but the chirality it has been changed. So substitution reactions of ammonia for both chlorides. Here we have two diethylene diamine En2 ligands are present and two chloride ligands are present. So they also involve a similar change in product, and it is dependent on the temperature. So when we take liquid ammonia at minus 33 degrees centigrade, then there is an inversion of configuration. But for both cases, retention of configuration takes place in liquid ammonia above 25 degrees centigrade, and sometimes the trans isomer is also present. So you see, when we change the reaction temperature, then the nature of the product that we obtain is also it is affected by it. So that is why the reaction parameters for the substitution reactions, ligand substitution reactions in square planar complexes, and particularly the temperature, it should always be taken into account. the experimental evidences, it have shown that mostly the conjugate based mechanism is the one which is followed for the inversion reactions. So as we have just studied now, then the configuration, it can be either it is retained or it is inverted, or we obtain the racemic mixture. But the experimental evidences, it has showed that the mechanism by which the inversion product is obtained is mostly by the conjugate based mechanisms. So in such situations, the configuration of the product is determined by the orientation of the entering ligand in the intermediate, which has supposedly the TBP shape. So but there are chances that other ligands may also decide its orientation. So as we see, whenever we have an inversion of product, so we have mostly indicated that it is due to the conjugate based mechanism, but sometimes it doesn't. Whenever there is also a ligand which influences the nature of the central metal ion, then we see the orientation also changes. So one of the common example is the beta form of the triene complexes is more stable than the alpha form. So here we see how the other ligands also, it influences the orientation and stability of the complexes. So here in this table, the table 3.1, we see the stereochemistry of acid equation. So you remember, equation reactions are those which where water is added to the uh, complex. So here you see CO diethylene diamine LX, where water is added, then one X, the X minus, that is anation reaction, means the X minus it leaves, and one H2O ligand, it goes into the coordination sphere. So from the stereochemistry of such acid equation reaction, that is in presence of an acid, suppose the L here is OH minus and X here is the Cl minus, then we can see 100% cis product is formed. So this is the how we can say the percentage of the trans product or the cis product that is affected by the nature of the ligand and the reaction condition, whether acidic or basic. So here in table 2.2, this is the stereochemistry of base substitution. So when we have this L and OH goes into the X is removed, and here the OH is substituted into the coordination sphere. Here there is also a possibility arises of the racemic mixture. Apart from cis and trans, then the percentage of cis and trans, then the racemic mixture is also it is also obtained. So the total cis percent can also be calculated from the starting material. So here in figure 3.2, you can see the stereochemistry of a substitution in a square planar complex when intermediate shows retention from A to C. So here in this case, the intermediate, the product, it retains its configuration. But here then the intermediate B, this is the intermediate. So the product C, so when we start with product A, the intermediate reactant A, the intermediate form is B, and in case C, you see the trans configuration is retained. But when the intermediate, it pseudo rotates, it rotates to D in this case, as it has been shown here, and then it inverts its configuration to the cis form. So you see how the stereochemistry of the substitution in a square planar complex when the intermediate is highly dependent on the intermediate retention. So you see, this is how the process is carried out. This is the mechanism. Then we'll talk about substitution in trans complex. So the possibility of another three dissociative routes may be there other than the conjugate base mechanism. So in last class and even today we have seen that conjugate base mechanism is the most probable for the that has been accepted as the most probable mechanism for the substitution of substitution reactions, whether in ligand substitution reaction in square planar complexes or octahedral complexes. But there are other mechanisms also possible. So a square pyramidal intermediate, it results when a living group X, it from the reactant it leaves out. So once a living group X, it goes away from the reactant, and that is from our starting material, and there is the formation of an empty space. So this empty space, it is fulfilled by the new ligand that we want to substitute, and therefore the configuration here, it is retained in such type of cases. So here in figure 3.3a, when we talk of this, is the when a square pyramidal, you see an intermediate is formed during the substitution process, then this is called as a square pyramidal structure. Whenever we come across a reaction where a substitution reaction which leads to the formation of a square pyramidal intermediate, then the final product that we obtain after the substitution, it occurs with the retention of the configuration. That is, if we have started with a cis product, then we will end up with a cis product, and if we have started with a trans product, then the configuration will be retained, and the product that will be obtained will also be trans in nature. So here the first figure, it illustrates this mechanism. Now when the intermediate is trigonal bipyramidal, that is TBP structure, if the intermediate is TBP structure with B in the trigonal plane, then both the trans and cis products are formed. So here that in 3.3b, you see whenever there is a possibility that the intermediate will be of trigonal bipyramidal structure, then in this case both trans and cis products are formed. So and what happens here, if in this case, so that is, if you look here in figure 3.3, we can also say that the products are cis isomers, but the possibility of cis isomers is also there by leaving the when the living group dissociates. So even when we look at this figure C here, in this case 3.3c, so one of the two, here also cis products are obtained in this case. So that is why, looking into the nature of the intermediate, then we can say what type of product is obtained at the end of the reaction, with the either with the retention of the configuration or with the inversion of configuration. So now let us look at the mechanism here which has been given in 3.3b. So here in 3.3b, we see this is a trigonal bipyramidal intermediate. So here two-thirds of the product, they undergo a configuration change from trans to cis, which is not much obtained as evidences. The retained ligand B decides whether the what would be the proportion of cis and trans product for the type of the reaction that is involved. Okay, and then we see that the mostly for but these cases two types of products are formed, that is the cis and then is the trans. We must also look at the isomerization rates for both the reactant as well as the product. So here when we look into table 3.3, this is the rate constant for the reaction of cobalt diethylene diamine and aqueous, and X is the ligand at 25 degrees centigrade. So here we can see that the rates of racemization and cis to trans isomerization are almost same. So here the rate of racemization and the cis to trans, here if we look in this example, here cis to trans conversion rate is 2.4, here it is 2.2 and 2.4. For water, then it is 0.012, this is 0.015. So here we see that the rate constant for conversion of cis to trans and the rate constant for the racemization reactions, they are almost same. So although water exchange is faster than other reactions for all, the hydroxide complex, when we look into the hydroxide complex, here for the cis to trans conversion, the rate constant is 200, that is per second. The unit of rate constant is equal to second inverse. So but there has been no rate constant observed for the racemization reactions. So here although the water exchange is faster, particularly for the hydroxido, that is the OH minus complex, it becomes a pseudo first order due to the presence of excess of water. So because of the presence of high amount of water in our solution, the K for the racemization, it is difficult to evaluate. Then substitution in cis complexes. So if we look into figure 3.4, here it has been shown figure 3.4. This is the substitution reaction. So there are three intermediates have been shown in the substitution reaction of cis complexes. The configuration is retained when the intermediate has a square pyramidal shape. If we take the case of the intermediate which forms as a result of dissociation of X, that has the shape of a TPP, that is trigonal bipyramidal, then the entering group is added to three possible sites. Of these three possible sites, one is a trans product and other two are cis products. So two cis products are obtained and one trans product is obtained. And in the third case, when the intermediate is trigonal bipyramidal with an axial B, which does not have much possibility, then a racemic mixture is formed. Configuration can be written for the cis complex, which is optically active and then becomes geometrically trans, or it may be a racemic mixture. But evidences have shown that the equation of 6MLL2BX, here it gives rise to 100% of cis isomers. So, which implies that the intermediate has the shape of a square pyramidal. So, here, although the theory talks of the possibilities of one trans isomer and two cis isomers, but the experimental evidences, they have shown the presence of only 100% cis isomer. And because of the experimental evidences, it was concluded that the intermediate here, as in the figure 3.4 that has been shown here, it occupies the square pyramidal structure. It acquires the square pyramidal structure. So mostly 97% to 66% cis products are formed when substitution of optically active cis complexes in base takes place with the when the configuration is retained. So here the products that are obtained, they are an equal mixture of cis and trans for the trans reactant. So this is a question that is based on the evaluation of the square planar substitution complexes. Then coming to isomerization of complexes with chelate rings. So complexes that have three bidentate ligands, they may undergo isomerization reactions by first dissociating one point of attachment. The five coordinate intermediate that is formed, it undergoes rearrangement and it further it undergoes rearrangement. However, whichever ligand it first rearranges and dissociates in the first step is the one that is incorporated back at the end. So here is one important theory, that is Berry's pseudo rotation mechanism. So this is a very important mechanism in substitution reactions. So whenever chelating ligands are present in compounds, then the mechanism of isomerization, it involves twists. So here if we look into the different figures, here it has been shown in figure 3.5, the different twists for different types of complexes, it has been shown. So here you can see how the twist it occurs. So the trigonal or Baylor twist here in this figure, in the first case, it is called as the trigonal twist. In the second case, it is called as the tetragonal twist with perpendicular rings. And in the third case, it is a tetragonal twist with parallel rings. And the D case, it indicates the alpha beta isomerization. So what are these? individually we will look into it. So first is the trigonal twist or the Baylor twist. So here two opposite trigonal faces, they are twisted, and the transition state, it is a trigonal prism and finally forming the structure. So this is a trigonal twist. So when we talk of a tetragonal twist, so it involves two chelate rings and forms a new structure while holding one ring stationary. So out of this, the stationary ring of the transition state, here it has been shown in figure 3.5b, it is perpendicular to the to those that is being twisted, and all the three rings, they are parallel in the transition state. So however, in the other twist that we have seen in the third case, that is the, it is very difficult to it is very difficult. So here it is, the basic difference here is they are perpendicular, and here in this case you see that is they are parallel to each other. So specific metals like aluminium, indium, chromium, they do not have the possibility of trigonal twist mechanism. So such type of complexes, they show trigonal twist from the conversion of the multiple ring structure of the alpha ring structure to the beta isomer. So this is the fourth twist, that is, that involves the conversion of the alpha isomer to the beta isomer. So this is this is the mechanism of twist for different types of twists for isomerization in substitution complexes, in square planar complexes. So now coming to substitution reactions of square planar complexes. So these are the certain possibilities we talked of. Now we will see the substitution reactions of the square planar complexes. So the configuration is retained in the products of substitution reactions of square planar complexes when the departing ligand is replaced by the new ligand. Both the entering and the departing ligands, they influence the rates much, and different compounds can be formed. So if we study the kinetic and thermochemistry and the stereochemistry of square planar substitutions, taking example of the reactions of platinum compounds that were studied in detail, we see that T to PT, T PTX plus Y, it gives rise to T PTY plus X. T is the transligand to the platinum, X is the ligand that goes away, and Y is the ligand that is being substituted. So from figure 3.6, here you can see this is the mechanism of interchange in square planar reactions. So for the first case, this is a direct substitution reaction. Here you can see this is the Y that enters here, and this is the X that goes away. Then the second case, this is the solvent assisted substitution reactions. So here S stands for the solvent. First here it is solvated here, then after solvated, the Y, it enters into the complex, and after it is attached to the complex, then here the solvent is removed and it goes away. So this is the solvent assisted substitution, and the upper one is the direct substitution. So we will discuss this in details. So we can see in the direct substitution, we can see the entering ligand, it comes along the z-axis, and after it is bonded to platinum, a 5-coordinate intermediate forms, which is almost a trigonal bipyramid with platinum, the T, X and Y in the trigonal plane. Now when the leaving group X, it exits from this, then all of them, they adjust into the same plane, and finally this type of product, it is formed. So here of this, the product that is formed, it is almost of the same configuration. So here this is sort of a IA mechanism. So it has also been happened that the ID mechanism, where the bond, it breaks, when the ligand breaks, it first becomes weak, and the bond with the incoming ligand also forms. So mostly the both IA and ID mechanisms can be associated with such type of substitution reactions. Then in figure 3.6b, we talked of the solvent assisted substitution reactions, as here it has been depicted here. Uh, so here the particularly the rate law for square planar substitution reactions, it has two terms, and it is represented as K1 complex plus K2 concentration of the complex into concentration of the Y. So here concentration of the complex means of that of the reactant, and Y is the ligand. So this is the concentration of the new ligand. So K2 supports the associative mechanism, whereas K1 is for solvent assisted reaction here, as it has been shown in this case. So after the incoming group Y, it replaces the solvent. Then since solvent concentration is large and it remains unchanged, so it is practically a pseudo first order reaction. So the second step of the mechanism may be faster than the first, leading to the approximately first order reaction of the complex. So mechanism of interchange in square planar reactions: direct substitution by Y, here the shown, and the solvent assisted substitution. So in table 3.4, the rate constants and nucleophilic reactivity parameters for different entering groups, it has been shown. This is trans platinum I2Cl2 plus Y. It forms the same configuration, that is trans platinum I2Cl Y2Cl minus. So this is the reaction with the same, having the same type of the configuration is retained in both the cases. So here it has been shown. So this table, if you look into this table, the L for different types of values, the rate constants and nucleophilic pathway parameters, it has been shown. In table 3.5, the rate constants for living groups. Here for different living groups, you can see for nitrite, Cl minus, bromide, and all these cases, the uh, uh, living groups constant, it has been shown. So factors affecting the reactivity of square planar complexes. So here there are some important factors which which influence the reactivity of square planar complexes, and particularly four important factors are there, and we'll discuss one by one. The first is the role of the entering group, the first is the role of the leaving group, the third is the effect of metal center, and the fourth is the nature of the other ligands that are present inside the coordination sphere around the metal complex. So these four points are very decisive in the reactivity of the square planar complexes. So first is the role of entering group. Here, if we look into the table 3.5, here it has been shown here. This is the table 3.5. This is the rate constant for different living groups, and you can see they are the rate constants are different. So we can see that the living group in the trigonal plane of the 5 coordinate intermediate, it influences the rate of the reaction. When we have hard ligands like Cl minus, ammonia, NO3 minus, then the order of X ligands is almost the opposite to that mentioned above. But when we consider soft ligands like cyanide, NO2 minus, that have significant metal to ligand pi bonding, the system, they go very slowly out of the system. So here, if we have an example, platinum di in X plus pyridine, it goes into this system and X is removed out of this system. Then if here X is H2O, then the rate of this reaction, it increases by a factor of 10 to the power 5. If we compare it when X is Cn or NO2 minus, but when the water is taken as a ligand here in the case of X, then the rate of the reaction, it increases. So we see the role of the entering group, that is which enters into the complex, is also it increases or decreases the rate constant. So square planar platinum complexes having metal to ligand pi bonding to X, they are much less reactive when these ligands are substituted. The P interaction, it makes the metal to X bonds stronger. So furthermore, the orbitals that bond to the entering group on the trigonal planes are also used in pi back bonding to S. So we can see that when pi bonding exists in metal to ligand bonding, they are displaced much slowly compared to ligands where sigma bonding is the only option. So now this is the Swain-Scott equation, which is the linear free energy relation, and it is given by this equation. So that is log base 10 ky by k0 is equal to Sn. So it is applied to a variety of reactivity of a given electrophilic substrate towards a series of nucleophilic reagents. So N, this N that has been represented here, it is the characteristics of the reagent, that is a measure of its nucleophilicity, and it is also a characteristic of the substrate, that is a measure of its sensitivity. So that is why it is S and N. So N measures the its nucleophilicity, and S it measures the sensitivity. A scale of n values there is a present, which is based on the rate coefficients for the reaction of methyl bromide with different types of nucleophiles in water at 25 degrees centigrade. So S has been defined as 1 for such type of reactions, and N has been defined as 0 for particularly the hydrolysis of methyl bromide. So from this sort of from this equation, the Swain-Scott equations, one can find the reaction rates if the values of S and N are known. So then we can find out what is the Swain-Scott equation constant. So here, when substitution occurs at square planar D8 complexes, it has been seen that the entering groups, they do not influence the rate of the reaction when the living groups. So this is because the platinum to the living group bond, that is the X bond, it breaks much easily, and it is more important than the platinum to Y bond formation. So the rate of substitution reaction for complexes that have poorer leaving groups, it is mainly influenced by other ligands which are bound to PT2. From equation 3.3, we can find that here we can find equation 3.4, which gives the value as log of ky is equal to Sn of platinum plus log of ks, where ky is the rate constant of the reaction, Ks is the rate constant of the solvent, and S, as we talked about, the nucleophilic constant, and here the sensitivity that or we call it as the nucleophilic discrimination factor, and here N is the nucleophilicity. So here it has been, this is the equation that has been shown here for the determination. So the nucleophilic discrimination factor, that is we call the sensitivity S, is defined as 1 for trans platinum dipyridine dichloro complex. So here for this equation 3.5, it gives the relation from which the values of NPT can be obtained with the kinetic data. Then coming to the role of the living group. So there is a significant evidence for a 5 coordinate intermediate, and with the help of the solvent, the transition state, it may be 6 coordinate also. So there are two possibilities for the highest energy transition state. One may be the intermediate form, or another, when the living group, it goes away from the intermediate. So we see that the incoming ligand, it influences the rate, because when we have the HSAB principle, that is hard soft acid base principle, then the soft ligands will react faster with PT2, which is a soft acid, but other ligands on the PT, it will definitely influence the order of the ligand reactivity. So here in this common equation, for this equation trans PtL2Cl2 plus Y, it forms the same retention of product trans PtL2Cly plus Cl minus. But when this Y group, the order of the order of the reaction, it varies in this order. Okay, so this is how the leaving group, it influences the rate of the reaction. Then coming to effect of metal center. So the order of reactivity of a series of isosolvents, isovalent ions is nickel 2 plus, which is greater than Pt2 plus, Pt2 plus. It is same as the tendency to form 5 coordination complexes. So for example, here you see nickel, K of nickel, it is greater than that of K of palladium 2 plus, which is greater than that of the K of Pt 2 plus. So here it is for isovalent ions, that is, since all are 2 plus, so it takes up the reactivity of these ions in the order they wish to form 5 coordinated complexes. Then the nature of ligands in the complexes, it also directs, or it also affects the rate constant, and this nature of ligands in the complexes have been categorized into two types. One is the trans effect and the other is called as the steric effect. So these are two, out of all these factors, this trans effect and steric effect are important because they influence heavily the rate constant of the substitution reactions. So first we will talk about the trans effect. So this trans effect, it was first described by Chernev, the ability of a group to direct the substitution into its opposite transposition. So that is called as the trans effect. So here this means that there is one group which is present and it will always direct the incoming ligand into its opposite transposition. So the trans impact, it is reduced when the rate of substitution in the trans PT2 complex, it decreases. For example, when we look at equation 3.6 given below, this is the trans complex that we are talking about. Now the pyridine will go into the complex and here the chloride will come out of the complex. So here if we look here, the pyridine, it goes here and the chloride comes here. So this is the transposition. So hence a trans product is formed. So with increasing trans effect, the ligands, they have the relative rates as C2H4, it is greater than NO2 minus, bromide minus, which is greater than Cl minus. But similar type of decrease in activation energy, it also happens. So we know that chloride has a larger trans impact than ammonia, and ligands trans to chloride, they are more readily replaced in reactions involving particularly Pt2 complexes. And we know that platinum 2 plus complexes, they are mostly square planar in nature. So the trans effect allows the formation of isomeric platinum compounds. Here in equation 3.6 it has been shown the order of trans effect ligands, it also has been observed in various types of compounds. The trans effect is rationalized by two factors. One is when the PTX bond, it becomes weak, and the other is when the 5 coordination transition state, it becomes stable. So here when we look into the figure 3.7, that is the energy profiles. So we can see the corresponding energy coordinate diagrams here and we can understand. So here particularly in the first case, you see this is the ground state, it has a low ground state and the energy of the transition state is much high. So that this is why this has a very poor trans effect. Particularly in the second case, this is the sigma bonding effect because the ground state has higher energy and this is the because of the influence of the trans effect. Particularly in the third case, we see this is the pi bonding effect and it has a lower transition state where this is also stabilized due to the trans effect. So here is the sigma bonding effect. Here it has been shown here. The case of B, it has been shown here. For strong donors, particularly for strong sigma donors, the PTX bond is usually influenced by the PTT bonds since they utilize the PTPX and dx square minus y square orbitals. So because the PTT sigma bond is strong, it uses a larger contribution of these orbitals and it leaves very less space for the PTX bond. So once the ptx bond, it becomes very weak. Its ground state, that is the sigma bonding orbital, it becomes higher in energy. So now this ground state effect is called as the trans influence. So then weakening is observable. Such type of weakening has been observable by different analytical techniques. Then what is this pi bonding in the platinum T bond? That is, this is the stabilization of the transition state. So electrostatic theory cannot explain the stability or the trans effect for the strong pi acceptor ligands. So the vacant pi to pi star orbitals of this pi bonding ligands to form the d orbitals, and it forms the metal to ligand pi bond. So this was actually suggested by Orgel. So when Orgel stressed on the fact that the transition state would become more stable, here the figure has been shown here, as a result of the pi bonding, because the activation energy, it gets lowered due to lesser electron density. Now when the energy of the transition state is lower, then the activation energy, it's get reduced, and this is the stabilization of state due to the pi bonding. So here the overall trans effect here is the result of the combination of two effects, and here it has been shown here. So the ligands which are in top of the series, they are arranged in this series, they are the top of the series, they are the strong pi acceptors, and then comes the strong sigma donors. So the ligands which are at the bottom of the series, they are neither strong sigma donors or pi acceptors. So here the rates are different, because much different, and they goes to an order of 10 to the power 6 for strong trans effect, in comparison to ligands which have weak trans effect. So now we'll just take a break of 5 minutes and again resume with the steric effects. So now we'll talk about the steric effects that influence the uh, rate constants of substitution reactions. So here we know that associative and dissociative mechanisms, they whenever there is a steric hindrance, associative and dissociative mechanisms takes place. So bulky groups, they cause steric hindrance at the reaction center, and therefore associative reactions may not occur. So the rate constants of the replacement of chloride by water in cis PT ClPet3 complexes, here it has been shown. So how this is for pyridine, then for 2-methyl pyridine, the because of the presence of a methyl group, there is a steric hindrance and the rate constant decreases. And for 2,6 dimethyl pyridine, so here two methyl groups are present, and the K value further decreases. So here when we move the series along this series, the methyl groups, they show steric hindrance and water cannot be attached as a result. So we see with the increase in bulky groups in the series, then the rate constant also decreases. So this has been clearly shown by this type, by the reaction here. The effect is smaller if L is trans 2 chloride minus. So the difference is explained by the fact that methyl groups being further from the entering and leaving groups in the trigonal bipyramidal transition state if the pyridine ligand is in the trigonal plane. So here it has been explained how 2,6 dimethyl pyridine trigonal bipyramidal state, they all with the trans effect. They here this is the trans effect, and here how they affect the steric hindrance and increase the rate of the reaction. So coming to the effect of solvent. So the effect of solvent will explain by taking this example in equation 3.7. So this is trans PT dipyridine dichlorocomplex, and the this is the Cl star. This has been the isomer, and this has been a star is given to identify. So here it goes into the, this is the substitution reaction. The solvents, if we take DMSO, water or alcohol, they have good coordinating ability and they do not influence the substitution of chloride ions. But substitution reactions in solvents with weaker coordinating capacity, like for example, CCl4, benzene, DMF, etc., they depend on the concentration of Cl minus. Then coming to effect of charge on the complex. The rate of substitution reactions, it decreases when the positive charge on the complex species increases. So a dissociative nucleophilic substitution SN1 process, it takes place with the reaction rate decreasing when the charge of the complex it increases. Then coming to the effect of temperature and pressure. The assumption is that the rate determining step of the square planar platinum 2 complexes, it is associative and is supported by negative volume of the entropy of activation. The entropy and volumes of activation for the reactions involving PT2 plus and AU3 plus complexes has been shown here in table 3.6. So here you can see this is the different, the K1 and K2 values, the del H and the delta S values, it has been shown here for different square planar complexes of platinum 2 plus and Au3 plus in methanol. So the temperature dependence of the rate constant, it yields the entropy of activation, which represents the change in disorder that is at the formation of the transition state. So similar to this, the volume of activation is the change in volume that happens upon the establishment of the transition state, and it is determined with the help of specialized equipment from the pressure dependence of the rate constant. Particularly in ligand substitution processes, the increasing molar volume is correlated with the limiting situations for the activation volume. So both the quantities given in the table, they have strong negative values throughout. And if you look here, they are all strong negative values throughout. This may be due to the fact that there is more ordering and volume also decreases as the entering group as well as the leaving group are present. So here it may be said that the rate determining step is associative in nature. So with this part on ligand substitution reactions in square planar complexes is over. These are the some of the questions associated with this chapter. The next chapter is the ligand substitution in octahedral and tetrahedral complexes. So here in this chapter, we'll talk about the trans effect and its application to synthesis of complexes and understand the stereochemical changes in substitution reactions of octahedral and tetrahedral complex. So we know that Alfred Werner was the first one to observe that certain complex ligands have the power to affect the reaction of groups opposite to themselves, and this principle was called as a trans effect. So from the studies of such type of platinum 2 complexes, then the polarizing theory was introduced. This was the first theoretical explanation of the TE, that is the trans elimination. So, according to this, a donor group that is stabilized by that is usually stabilized, it causes a buildup of negative charge on the metal, which tends to repel the the negative charge on the trans ligand and weakens the trans bond. Later, an electrostatic perspective provided a clear picture of dipoles and induced charges. So here, this theory, it first explained the particularly the trans elimination, that is we term it as TE, and this was explained by the particularly by Greenberg, who explained this theory. Later, an electrostatic perspective provided a clear picture of dipoles and induced charges. It was found that the metals with the largest TEs are also the ones that create the greatest number of covalent metal ligand connections. Hybridization at the metal was therefore considered by Sirkin, who suggested that opposing metal ligand bonds will compete for the available s and d orbitals. So this model, it emphasized on cis stabilization and not trans stabilization while trying to explain the TE. So, but when only in the above case, only the sigma bonding was taken into consideration, even though there were indications of other bonds. For example, phosphines, they showed strong sigma inductive effects. So the strong sigma inductive effects, they have been mostly shown by the phosphine ligands. So subsequent efforts to refine the current theory, they were undertaken by Chat et al. And Orgel, who made the crucial move of taking metal ligand pi bonding into consideration. So it was Orgel who talked about metal pi bonding here in complexes, and then he was the pioneer in developing the Orgel diagram, which further explained the stability of octahedral substitution complexes. So Chat and Orgel explained this by citing the stabilization of transition states, that where the ligands, they act as the pi acceptor ligands. But it was in 1961 that Basolo et al. Had found this model. It could not explain the KTEs, particularly for they are observed for ligands like such as hydride and Me minus. So usually then, according to the standard molecular orbital study for the octahedral complexes, the trans ligands which share the same metal orbital is not much favored energetically. So if they are forced to do so, then one metal ligand bond, it will be weaker than the other. So in these cases, the earlier polarization theory has been substituted by quantum chemical calculations and DFT theory. So, the impact of coordinated ligand on the lability and the metal to ligand bonding of other metal ligands in a complex, it has been taken into account. A trans effect has been defined as the effect of a coordinated group on the rate of substitution reactions of ligands that is trans to itself. So it is a kinetic phenomena. The term trans influence, it was used to describe the tendency of a ligand to selectively weaken the bond which is trans to itself. So this a particular tendency of one ligand to weaken a transposition trans bond that is opposite to, that is present in transposition, it was first called as trans influence, and it is commonly used to describe the ground state phenomena. Even though we use bond weakening as same as the bond lengthening, we should understand that it is not the same always. So no solid ground state is there as to why effect should be a kinetic property, whereas influence should be a thermodynamic property. Till date there has been no explanation, and also that is why we generally talk of trans effect, but there are certain ambiguities that is associated particularly with the term. So thus particular expressions have been introduced. One is called as the STE, that is structural trans effect, which means the effect of the ligand on the bond distance to a trans ligand, and kinetic trans effect, that is the effect on the lability of the trans ligand. So these have been studied well in octahedral transition metal complexes having d orbitals. So let us understand the way different ligands they affect the structure and reactivity of these complexes. However, we should first look into the classification of ligands, and particularly octahedral complexes they are more common, so their behavior is mostly classified on the nature of the ligands that form an octahedral complex. So first is classification of ligands. So ligands are classified based on their trans effects into three main classes. The first is the very large STE ligands. These ligands are SiR3 minus and NO minus. They show significant trans effect when they are compared to chloride minus. So that is why they are called as very large STE. Then comes large STE. So they are the ligands like H minus and R minus, and they show moderate trans effect. So that is the structural trans effect is moderate in nature. Then comes the moderate ST ligands. So this group it includes ligands like carbonyl and cyanide, and they show very small trans effects. So here, based on the trans effects, we see there are three types of ligands classes: very large ST ligands, large ST ligands, and moderate ST ligands. So now we will look into the saline features of these ligands. The mutual nature of STs, some ligands like NO plus, that is the nitrosin, it demonstrate varying trans effects depending on the type of the ligand they are paired with. For instance, they show moderate STEs when trans to pi acceptor ligands, and negligible STEs when they are trans, they are present in trans to sigma donor ligands. So you see, this is the nature of the mutual nature of the STE. Then dependency on the metal center. The trans effects it can vary based on the electronic properties of the central metal atom. For example, pi accepting ligands they show moderate STE, but in D0 complexes their effects are weaker than those of chloride minus. So here we see the configuration of the d electron, particularly the metal d orbital. Here the configuration also affect the STE. Then the correlation between STE and the structural TE and the kinetic TE. So the relationship between structural and kinetic TE trans effects is discussed. It indicates that they often correlate due to the nature of ligand substitution mechanisms in octahedral complexes. So ligands like nitride M3 minus and sulfide they have been used to illustrate this correlation. That is, they are correlated, particularly in an octahedral field, they are correlated to the nature of the substitution mechanism in an octahedral complex. Then comes the impact on transition states. So the destabilization of the ground state caused by STEs, it is likely accompanied by stabilization of the transition states during ligand substitution reactions. Then the implications for ligand design. So these insights may give clue as to how to design new ligands and understand their behavior in coordination chemistry. So once we know that how different ligands they affect the trans effects, then we can predict the stability, their mechanism, and the reactivity of the octahedral complexes that results. Then the structural and trans effects in octahedral metal complexes. Then IR and NMR spectroscopic measurements, they are among the several physicochemical techniques that have been used in the study of ground state trans effect. However, sometimes the data is not very clear. So, because of this, the particular there has been an instrument which is used for this is the X-ray crystallography. That is the single crystal X-ray crystallography, and it is a clear. It provides clear information on the STE, that is the structural trans effect, particularly for octahedral complexes. So, for such cases, let us consider one example. We will consider the ligand NO plus. NO plus is unusual in being the only ligand which is known to exhibit very large range of STE, which clearly correlates with the nature of the transligand. So inverse STEs were predicted to occur because NO plus is a weak sigma donor and it does not compete with the transligand. We know NO plus is a weak sigma donor and it does not compete with the transligands for sigma electron density. But from the molecular orbital theory, it was later suggested that the pi donation from the transligand is also important. So this is also consistent with the absence of any STE with ammonia or amine and the inverse of STE with such as chloride or hydroxide ions. NO plus nitrosyl is a strong pi acceptor. So it enhances pi donation by the trans ligands leading to stable structures. But this does not always happens. So sometimes nitrosyl trans to itself or to other strong pi acceptor ligands such as vanadium pentacarbonyl nitrosyl is found to be quite unstable in nature. So the experimental data clearly shows that the relative STs of the closely related NO plus and CO ligands, they have a very striking difference. That is the difference between our ruthenium OH2 bond distance in some complexes and in certain carbonyl nitrosyl complexes is much contrast. So structural studies with the complete series of 9 complexes, here it reveals that the trans metal to carbonyl bonds, they are shorter than their cis counterparts. This is because the EPH3 ligands are weaker pi acceptors than CO and also compete less effectively for pi electron density. So here this is figure 4.1. This represents the orbital representations of the bonding in linear metal nitrosyl complexes with different types of transligand. So here it has been shown in the first case, this is the sigma donor NH3R3. Here this is the sigma donor and here the trans bond is unaffected. In the second case it is the sigma donor pi acceptor cn ligand and here the trans bond is lengthened, and in the third case it is the sigma donor pi donor cl minus, then here the trans bond is shorter. So here we can see how the bonding in metal nitrosyl complexes with different types of the trans ligand, it influences the trans bond. So table 4.1, we see some octahedral complexes of transition metals that show trans effect. So here it has been shown some examples. Here these are the trans effects for certain octahedral complexes. So from the available data, we'll not be able to find any periodic trend between any atoms. So it has been found that the trans bis structures, they are more common, and STE of tertiary arsine or stilbene ligands is also difficult to find. But there are certain, the XRD, that is the X-ray crystallographic data, they show some of the bond angles or the bond lengths of the trans certain chromium complexes. So the data has shown that the chromium PPH3 bond, that it lengthens steadily as the pi acceptor strength it increases in the order, the difference between the strong sigma donor and the strong pi acceptor being 0.07 angstrom. So supporting the pi bonding theory, the chromium X bond is strengthened and the shortened as the trans CrPPH3 bond is changed. So then coming to the kinetic trans effects in octahedral metal complexes. So even though a STE destabilizes a complex in its ground state, this will only increase the reactivity in response to ligand substitution if the transition state's energy is unaffected. So dissociatively activated substitution can occasionally exhibit this, in which the STE and KTE ligand series of a given compound will resemble one another. There might not be a relationship between STs and KTs, though if the ligand in question has an impact on the transition state energy. So STs are always mutual effects, that is, the structural transition effects, the structural trans effects of a given ligand, it depends upon the bonding properties of the ligands being affected. For example, the nitrosyl ligand, it shows moderate STE when trans to pi STE. So thus, in this section, the trans effect and its application to synthesis of complexes, it has been discussed. Now we will talk about the stereochemical changes in substitution reactions of octahedral and tetrahedral complexes. So here we will study how the substitution reactions of octahedral complexes, they cause stereochemical changes. So the majority of the complexes formed by the transition metals, they are octahedral. So before we be beginning, we would see the general features of octahedral complexes. So most of the research on substitution of the square planar complexes has been done with platinum 2 plus. So compounds of this ion, they combine with several factors like they are favorable to kinetic studies because they are easily prepared, their reaction is so. Similarly, in kinetics of octahedral complexes, they have been mostly studied with CO3 plus ions, because that is also CO3 plus complexes are very well known and they undergo reaction at convenient rates. So the reaction of square planar complexes, they occur by associative mechanism. Only a very few dissociative mechanism is known, but when we talk of the first row transition metals in octahedral complexes, CO3 plus, it occurs by dissociative mechanism. So here this change from A to D activation, that is from associative to dissociative activation, is not surprising because we know that from square planar to octahedral complexes there is a change in the coordination number. However, evidence has been accumulating in recent years that substitution reactions of complexes of trivalent ions except for CO3 plus, it also occurs through a IA mechanism. So we will now consider additional evidence used to support mechanistic arguments in octahedral substitution reaction. So the ligands and the degree to which the four ligands that make up the square of the square pyramidal, square planar, they they determine the configuration. So in an octahedral complex, it loses one ligand to yield a 5 coordinate transition state whenever the dissociative mechanism it occurs. So then the incoming ligand, it fills the empty site. So ligand field theory has been basically understood by this mechanism. So the difference in LFSE, that is the ligand field stabilization energy uh, between the octahedral reactant and the intermediate, that is the transition state, have been calculated. So here figure 4.2 has been shown the change in energy levels from ligand dissociation from ML6 to square pyramidal ML5, and this is how these are the T2G and EG, and the change in energy it has been calculated. So the challenge is now to assess that the geometry changes from octahedral to C4V. Then the splitting of the molecular orbitals it takes place where there is a high D orbital. So the pattern for this splitting it will depend on the ligands, and also the how the four ligands that comprise the square of the pyramid it bends away from the axial ligand. So a new term is the ligand field activation energy, that is called as LFAE. It has been given in table 4.2. It is defined as the difference between the LFSE of the square pyramid intermediate, that is the transition state, and the LFSE of the reactant that was present initially. That is, the LFSD is the difference between the octahedral ML6 minus the square pyramidal ML5. So we will find that the ligand field activation energy, that is the LFAE, for the trigonal bipyramidal transition state and for square pyramidal transition states, they are almost similar. So we can understand in a better way the relationship of electronic configurations in octahedral complexes. The value of LFAE, it shows that for D3 and low spin D4, D5, D6, they are the most positive. So the octahedral complexes of these ions, they also predict very high activation energy. These ions are called labeled as labile when the LFA values are negative and the activation barriers for dissociation are predicted to be low. Usually, when we have D8 complexes, they do not follow this rule, and that is why D8 ions they usually do not form the octahedral complexes. So, because of the LFAE, and they do not bind by these rules. So here in table 4.2, you can see the different types of LFAE. So this is first is the octahedral LFSE. Here it has been shown. The square pyramidal LFSE it has been shown. So then the difference is calculated between this, which gives the LSAE. This is for the weak field ligand and this is for the strong field ligand. So for square pyramidal transition state, LFAE is equal to square pyramid LFSE for sigma donor only. So the substitution reaction rates of octahedral complexes, they may be affected by the electronic and steric factors too. So some of the cases where dissociative mechanisms for ligand exchange have been discussed. The oxidation state of the central metal ion, so slower ligand exchange rates are exhibited by those central atoms that have higher oxidation state. Then the second factor is the ionic radius. So smaller ions, they have slower exchange rates. The higher electrostatic attraction that arises between the central atom and the ligands is the reason for the above two trends. So if there is a very strong electrostatic attraction, then bond breaking between the metal and the ligand that is leaving, it will slow down. Okay, so the half-lives of for MH2O6 they are less than 1 second. The relaxation methods have been used to measure for such fast reactions. The aqua complexes of alkali metal cations they have half-lives of 10 to the power minus 9 seconds. So if we compare aluminium 3 plus whose half-life is 1 second and chromium 3 plus whose half-life is 80 hours, then we say that chromium 3 plus is an inert ion. So now let us look at the situations that predict a dissociative mechanism. So variations in the incoming ligand only marginally alter the rate of the reaction. So the rate of the annation means the addition of the anion, and equation means and substitution by water, they are often similar. So here the data, it has been shown here in table 4.3, that is the rate constants for substitution of nickel H2O6. So making the charge of the reactant complex more positive, that it decreases the rate of the substitution. The electrostatic attraction between the metal and the donor atom of the ligand, it increases as the charge of the complex becomes more positive. the steric crowding on the reactant, it increases the rate of the ligand dissociation. Then the rate of the reaction, it correlates with the metal ligand bond strength of the leaving group, that is LFER. The activation volume, that is the change in volume from the activated complex, is measured by how determining how much rate constant and the pressure is changed. Now let us look into an example how ligand substitution in tetrahedral complexes, it causes stereochemical changes. So here one of the examples, here it has been shown here in figure 4.3. So mostly, particularly in a tetrahedral complex, the ligands, they are packed very tightly. So this geometry is found to be altered, and squashed, the D2 geometry is found particularly in anionic complexes and uncharged complexes. Out of this, it has been found that D7 electron, they have the center where tetrahedral geometry is least preferred. So when we look here into figure 4.3, first case, we see there is an inversion of configuration. So inversion happens when substitution occurs with a good leaving group and the intermediate has the shape of a trigonal pyramidal. But the entering loop and leaving groups are in axial positions. So, but the case here changes when we have a poor leaving group. So here in the second state, if we have a poor leaving group, then the product is formed like this. So in the second step, the arrangement here, in particularly in B, you can see how the arrangement here it has been done, and this is the case of C with the retention of your complex. So sometimes much effective interference of the solvents can take place. For substitution in this type of complex in acetone, it follows the mechanism of association, but in methanol it follows a solvolytic pathway. So the nature of the solvent during the substitution reaction also affect the stereochemistry, and they have been illustrated in these reactions. So here most of this reaction mechanism and the kinetics have been studied by NMR spectroscopy, because it provides a very easy method for detection of such type of species generation during the reaction. So here in table 4.4, you can see the relative rate constants for various nucleophiles towards different substrates. They have been listed here for particularly, and the values have been listed. The metal carbonyls, they follow first order processes, but metal carbonyls, they follow the second order process, but they are mostly pseudo first order, they have been labeled as. So here all the rate laws, it has been used, and the scheme 4.1, you can see the mechanism for the solvent path has been shown for the catalysis of FeNO2CO2, that is the mixed nitrosyl carbonyl, and how the solvent path where it proceeds by a carbonyl attack. Here B is the solvent or the catalyst, and canonical structure where the B, it gets attached and has a positive charge. Here you can see in this step B has a positive charge, the solvent, it acquires a positive charge, and it has the possibility of stabilization as a result of the formation of strong pi bonding NO groups. So this happens as the electron density of the iron, it gets delocalized. So here this is one method of, this is one case of which explains the nitrosyl carbonyl mechanism by the carbonyl attack. So solvent pathway. So with this is the end of this unit on ligand substitution in octahedral complexes. So this much for today. Next class we'll start with a new chapter.
Thank you, ma'am.